Hello, good morning. Good afternoon, ladies and gentlemen. My name is Inigo Cuinas. I'm professor at the University of Vigo in Spain. I think it's better. And it's my pleasure to chair this session on electronics. I will try to do my best in pronouncing the names, but please, I'm sorry if I'm not able to do perfectly. I think the first presenter would be happy, because the first presenter is Pablo Corral from the Universidad Miguel Hernández de Elche in Spain. You know that Spanish names, I'm good doing that. The rest, I'm not sure. And it's your time. As we are the 5 persons, we have around 18 minutes to do to each presentation. So probably 15 minutes for presentations and 3 for questions. Is okay? Okay, so Pablo, the floor is yours.
Hello, everybody. So the name of the paper is Improvements of Organic Photodetectors for VLC using a new active layer, focal length, and transimpedance amplifier. So first of all, we are going to speak about an introduction about this topic. And after that, we are going to explain the different materials and methods that we are using in this research. And finally, we are going to show the main tests and results. So the idea of the use of visible light communication is an interesting technology for future communication, for instance, for 5G, and is based in the use of the visible range using light emitting diodes, LED, and can be considered an alternative used in the Internet of Things. Yeah? So the problem could be in the part of the reception. So there is, because of the lack of photovoltaic devices for this specific use. And organic photodetectors could be a potential in this kind of system because of the simplicity and low cost of these devices. In our case, in this research, the use of organic materials permits create a low-cost VLC system with wide availability, is commercial deployment thanks to the integration of a self-powered organic photodetector. This system, for instance, is not affected by ambient light or other interference. The range of power consumption, as well as the low cost, make them attractive attributes for mass manufacture and IoT devices. In this research, we are going to describe the main obtained results. If we compare with our previous research that we call OPD1, and the use of new active layers or adding a new transimpedance amplifier, and these results were called OPD2 and OPD3, respectively. So in the part of materials and methods, the idea in this research is to present 3 different experiments. And in the first one, we change the concentration of the active layer. In the second one, we add a focal length with the intention of collimating the beam. And in the third configuration, we add a transimpedance amplifier in order to increase the received voltage. So in the first figure 1, the experimental system is supposed to be able to detect the VLC without improving both the maximum allowed frequency. And in this figure, we can see the self-powered organic photodetector, OPD, using different cells. Yeah? And the diameter could vary between 3.5 millimeters to 4.5 millimeters. we have used a commercial LED, a high luminosity LED, very cheap, about 20 cents, something like that. It's a white light phosphor based LED with a correlate color temperature. And on the one hand, to generate the signals, we have used an arbitrary waveform generator, AWG, sorry, with a bandwidth about 12 megahertz and a sample rate of 100 megasamples. In the reception, to detect the signals, we are using a real-time oscilloscope with a bandwidth about 30 megahertz, 100 megasamples per second. So you can see the first configuration, very simple, using a commercial LED and our OPD, yeah, with different size of the cells. To find out the farthest distance, in the second configuration, the idea is to add a focal length. Yeah. So in the second configuration, we are using a different system to detect, to create the system, to detect the system. So first of all, we are using a Atmega 328 microcontroller in the transmission with an input to with a frequency of 1 kilohertz using a Manchester coding, a simple binary phase shift keying. And we can see in the second figure that we add a lens with 13 millimeters of focal length and a diameter of 2.54 centimeters. And in resection, to detect and acquire the transmitted signal, we use also an Atmega 328 microcontroller. So in transmission and reception, we have the limitation of the system. So in that case, the clock rate is 16 megahertz and only 10K samples per second. So in the second experiment, we use these devices, yeah, in transmission, in that part, and in reception. And finally, in figure 3, we can see the block diagram using a transimpedance amplifier. In that case, we are using an operational amplifier chip LT1028. So in this case, the configuration is very similar to the second place. So we are using, well, it's a mix between the first and the second experiment. So in the transmission, we are using an Atmega. And in reception, we are using a real-time oscilloscope. So in that case, we can improve the bandwidth in reception because we can use a bandwidth about 12 megahertz and a sample rate of 100 megasamples per second. Well, here we have a video that if we have time, maybe we can show at the end of the presentation. It's about 4 minutes. And this the explanation of the fabrication of our OPD. But more or less, this is the explanation of the video, if it's not possible to see. So first of all, the substrate was commercial glass with a thin layer of iridium, tin oxide. They were cleaned by ultrasonic chemical bath. Finally, they were submerged into 1 to 4 trichloroethane, acetone, and isopropyl alcohol for 20 minutes, and then dried with nitrogen. The P.PSS was spin coated at 7,000 RPM onto a glass ITO substrate. In all organic receptors, P.PSS was employed as the whole transporting layer. Then the P.PSS was dried at 120 degrees for 1 hour. P3HC PCBM blend was used as the active layer. They were dissolved in chlorobenzene at 10 millimeters. So this is the first difference between this explanation and our first experiment. In our first experiment, we changed the concentration from 10 milligrams to 20 millimeters. Yeah. Well, after that, the active layer were spin coated at 500 RPM and dried at 80 degrees for 1 hour. Finally, metallization was performed employing aluminum. It was evaporated in a high vacuum chamber until the layer reached 200 nanometers. After metallization, an annealing ramp process was started. The device were heated to 120 degrees. And when the temperature was reached, it was safe for 2 minutes. Subsequently, the device were allowed to cool to room temperature, about 25 degrees. Well, the characterization, we need to characterize our system. So in all of the research, we are using a high luminosity white LED, but we can compare this LED with different LED. So in the next figure, we can compare this different LED that we are using in the previous research. And in the next table, we can observe the results related with fall width at a half maximum and the value of the irradiance if we compare with a commercial OPD. So first of all, we can observe different LED, and our LED is a commercial LED. Yeah, it's not important, but it's the dashed line, this one, high luminosity white. Yeah. In the first table, we can compare these different LED, blue, low luminosity, high luminosity, green or red, related to emission peak, fall width at half maximum, and irradiance if we compare with commercial OPD. And we can obtain a characterization if, related with the curves of current density versus voltage. In that case, the most important values is related with efficiency and the rise time, because if we know the rise time, we can obtain the bandwidth of our OPD. And now the part of the results. First of all, we are going to compare the results in this research with the previous research. Yeah, so we can improve the results not only in the same frequency, 1 kilohertz, than also in 2 or 5 kilohertz, and with different distance. So we have an increase about 269% at 1 kilohertz, and we can obtain best results also at 2 kilohertz and 5 kilohertz. And we can increase until 7 centimeters the results between transmitter and receiver, for instance. Well, the use of RTO, the real-time oscilloscope, is important because with the histogram, it's possible to obtain the quality factor of our received signal, because we can obtain the value. So 2 minutes, yeah, I can do it. Because with the histogram, we can obtain the half width at half maximum and the value of the for level 0 and 1. We can obtain the Q factor, and with the Q factor, we can obtain the bit error rate, optical bit error rate. So here you have the results related with the bit error rate when using the first configuration. The second configuration is adding a focal length, and in that case, we can obtain an improvement in lower SNR. Yeah, it's important that we need to put the lens at 3 centimeters to collimate the beam. Yeah. So in that case, the results are very interesting in that part. And finally, in table 3, we can see the obtained result for the third experimental using a transimpedance amplifier. This amplifier is permit to increase the current output of devices to a usable voltage. In our case, we can obtain good results when you have small distances. Yeah. When increase the distance, increase the noise effect and decrease the effect of the voltage. So finally, in this research, we have shown an improvement of VLC using an ultra low cost LED in transmission and different upgrades in reception using a new active layer or adding a focal lens or inserting a transimpedance amplifier. In the basic structure of the OPD, we have improved its classical limitation by introducing changes in the active layer. So we can increase, in that case, until 269% in maximum voltage in the first configuration, or we can increase the distance until about 6, 7, or 8 centimeters. Using focal lens, we can improve the results in bit error rate in lower SNR. And using a transimpedance, we can increase the maximum voltage only in a small distance. And that's all. Thanks.
Thank you very much. We have a couple of minutes for doing any question if you want. So we have a couple of minutes for doing any question. Any question from the audience? If no, I have a question. Well, not strictly a question. It's more a curiosity. Well, the research is focused on improving the performance of VLC systems in order to be implemented in IoT or any other application. But we are in the range of some centimeters. So in your opinion, which distance could be the target for this kind of technology to be really useful for these applications?
This part is important, and the effect of the distance is due to the effect of using a very simple LED. Yeah, if we put a commercial LED using in a home, we can obtain best result in distance. But we are using a LED about 5 millimeters, very simple. Yeah, so because the idea is to obtain a very low cost system. Yeah, in transmission, about 10, 20, 30 cents, the cost of one LED. And the reception, we create the OPD. Yeah. So in that case, the idea probably could be interesting to use in a factory, because we need to detect when you have a communication or not. Yeah. And you are not interested in distance, but you are interested that the system could be useful in a critical environment that is not possible the use of the cable, or maybe the use of wireless communication can interfere in our machines. So this is more or less the idea of this system.
Okay, thank you very much. And any question from the audience? No? Well, so this is the end of your presentation, and
okay.
we'll move to the second one. Thank you.
Okay.
So the next one, the second presentation of this session is called Analysis of LoRaWAN Transactions for TEG-Powered Environment Monitoring Devices. And the presenter is Michal Prauzek. Thank you. From the Technical University of Ostrava in the Czech Republic. The floor is yours.
Okay, I'm happy to be here in person. So my name is Michal Prauzek, and I'm coming from the Technical University of Ostrava. And my paper is called Analysis of LoRaWAN Transactions for the TEG-Powered Environmental Monitoring Devices. So what is the point of this paper? We try to analyze of wireless transactional features. So the LoRaWAN is the wireless communication. So we want to know some parameters and its consumptions, like the spread factor, bandwidth, and so on. For this purpose, we built the custom embedded hardware, and we aim on some modularity. So the final platform could be used for other purposes to test another communication such as Sigfox, lightweight, and etc. So we want to optimize the payload, the transaction payload, and we want to know what energy we need for the transactions. And our target area is the environmental monitoring. So we want to construct some monitoring device to monitor the environmental parameters such as CO2 or solar radiation and so on. Our research area is in many places. So we are working with the environmental monitoring systems, as you can see in the figure. So we are working with the harvesting sources, power supply modules, energy storages. We do some measurements, so we have to do some signal conditioning. We have some processing in the microcontrollers, data storages, and this work is aiming on the communication modules. So in this work, we want to know what energy we need for the LoRa transactions. So the fair question is why we are analyzing the LoRaWAN transactions. In our lab, we are working with the rapid prototyping system. So the point is we want to design something in the simulation and we want to test it on the historical data and evaluate if it is possible to operate in the field. So in general, we want to obtain the parameters from the signal processing, for the control of the systems and the communication interfaces, and simulate the real case in the application. In general, the LoRaWAN power consumption is not straightforward. So we can read the data sheet and say the energy is maybe 10 milliwatts or something like that. So because we have many variables, like the regulatory policy, target payloads, transmission power, modulation parameters, power voltage, and so on. So as example, this is the case as the LoRaWAN consumption looks like. So you can see in the time we have different frames. And first big portion of energy is consumed by the transmission. And then we have the two windows to receive the data. So we can use only the one window, or we can use the second window also. We already try different configurations. So we can modify the transmission phases. And we can adjust the transmission power and data rate. So the data rate, as you can see, data rate is a combination of the spread factor and the bandwidth. And it's some kind of effects of the regulatory domain. And we tried the data rate 0 and 2. And also we can try some modification on the transmit power. And we tried the transmit power 0, 3, and 7. This is our platform. We built it. So this platform includes the custom board, which allows some control of the measurement and also allows some advanced current measurements by the current probes. We connect the DC-DC part, the DC-DC converter, and also we connect the dev kit of the LoRaWAN, but we can connect any other communication interface. This is our idea of the firmware. So we implement some basic firmware. We just have some user trigger to send the transactions, and then we are waiting for the receive. And if some error would happen, we can catch it in the error handling procedure. So this is pretty simple hardware and software, but the point is to analyze the current in the circuit. So we did this measurement setup. As you can see, we have the LoRaWAN Semtech module, and it's connected to the Freescale KL25Z MCU by the GPIO and SPI interface. And then we have the In the bottom part, we have the key site. It's a 10-bit oscilloscope. It's pretty high ranking. And we are using the advanced current probe key site and also the one channel to measure the voltage and the marker if the transaction can receive. So this is for the various experimental measurement, and we are using the different configurations. So this is the result. So we have several results for different, for various power supply. And we have the different takes power, also the various payload, and we have the result of the final energy consumed during the transactions. So you can see the results in the time domain. On the left, we have the current in the time with the various transmission power. So the blue one is transmission power 0, the red one is transmission power 3, and the yellow one is the transmission power 7. So you can see that the transmission power affects only the transmitting data, but you have the same energy for the receiving. And on the right, there is the sample of the data rates. So you can see the sample of the data rate 0 and 2. The 0 is the blue one, the 2 is the red one. And the data rates affects the duration of the transactions. So as you can see, the data rate 2 has the small amount of energy to one transactions, but it has the lower distance to reach with the signal. So this is the summary of the comparison on the power voltage. So you can see, of course, the lower voltage, then you have the lower incoming, the consuming energy. Data rates affects also the duration of the transactions. So the energy corresponds with the data rate 0 and 2. And the payload, we test the payload, the 8, 20, and the 32 bytes. As you can see, the 32 bytes is the higher consumption, but it's not as 4 times than the 8. So the payload, it's just a portion of the all transaction of energy demands of the all transactions. So the conclusion. In this study, as I said, we try to estimate the amount of energy need for the transactions. And we built some custom hardware to test it. We state that the data rate affects the final amount of energy, also the transmit power, but only in the part of the transmitting, not the receiving. And the last one, the results are useful mostly for the simulation that leads to the rapid prototyping, and we can test the device in offline way, and then we can build it and it works as we expected. Okay, so that's it. Thank you.
Okay, thank you very much. We have time for questions. Any question from the audience? So it's possible to have questions from people online? Well, the audience is then extended to the online people. No questions. Okay. I was thinking my question, but it's not no. For me, it's not easy because I'm not an expert in this field. But assuming that I can ask some stupid thing, is that once you have the evaluation of the different impact of changing different parameters or different configurations in the total energy consumptions, Did you compute or prepare some kind of equation, formulation, guidelines in order to look for optimizing the energy consumption in terms of the different configuration for different cases of application, or this is the next step?
Yeah, it's a more like next step, because in the first stage we want to get the results, what energy looks like, and in the second step we want to include in the simulation, and this simulation can result in the set of parameters for the real application. That's the point.
Okay, thank you very much.
Okay, thank you.
Any question? Additional? Oh, yes.
Since you spoke about DC-DC converters previously, also during our discussion, how big is this converter? Would it fit in 1 centimeter square space?
I think we are using the LTC, the linear solution. So it's, I think it's SO8. It's around 5 millimeters times 5 millimeters, but you have to implement on the PCB. So if the PCB is the complementary set with your harvester, it could be possible. But in any case, you have to implement the circuits, the capacitors, and so on around it.
Okay.
But it's for the TEG application. So we are using the boost, and also as we talk at the lunch, we are also using the boost topology. So it's possible.
Okay. And the plan to optimize or to balance the impedance matching. Basically, in all harvesting systems, the biggest problem is impedance matching. So do you use MPPT technique to optimize this impedance? Not optimize,
of course, you have to use the MPPT because you have to get the enough energy, because as you know, the harvesting topology has a small amount of energy and you can waste it. So you have to use it. But in this case, we are using the standard tracking. We don't have such specific solution for the low energy harvesters.
Thank you.
Okay, thank you very much. Then thank you. The third work in this session is open source hardware cost-effective imaging sensors for high throughput droplet microfluid system, and is going to be presented by Kaiser from the Tallinn University of Technology in Estonia. So the floor is yours.
Yes, hello everybody. My name is Kaiser and today I will talk to you about open source hardware cost-effective imaging sensors for high throughput droplet microfluidic systems. Before digging into details, I will briefly cover the outline. I will talk to you about, in a few slides, where I'm coming from, about Tallinn University of Technology. On a few slides, I will present what a typical microfluidic system looks like, because I assume that most of you maybe don't really know what it is. So just a brief overview. Then I will present what we were actually using in our setup. As we have established the background, I will talk about motivation, why this research was necessary, what I found, what the results were, and then let's end with a small conclusion. So the Tallinn University of Technology, to my knowledge, the only technological university in Estonia. Last year we had roughly 9,000 students. We have roughly 2,000 employees working in the university. Last year we published around 1,400 publications, and so far over the time we have almost 80,000 students who have graduated. So if you are very interested, please come visit us in Tallinn. Now more about the topic. To better understand what I did and what the paper was written about, I will try to give you a short answer that why the microfluidics or even droplet microfluidics is necessary at all, and why is it interesting to scientific community. So why microfluidics? If we are talking about experiments that the doctors do in the laboratory, they are using syringes, they are using some vials, they took some reagents, and what is the problem is that whatever reagents they are using, in some cases the reagents can cost up to thousands or 10,000s of euros per milliliter. Imagine, milliliter is a quite small unit. So the first sort of benefit of microfluidics is that it tries to minimize the reagents that will be used, meaning that the size is small, the reagent used is small, and this also leads to a reduced cost of materials used. Now, if we talk about the droplet microfluidics, I will show you one example later on that you understand maybe a little better what the droplet microfluidics means. Is that there are separate fluids pushed together into a very small area. And what happens is that droplets form. Inside the droplet becomes a sort of micro reactor. We can put into the reactor whatever we want. A very good example would be just let's put some virus inside or pathogens inside together with antibodies, and let's see how the reactions take place. Why do we want this kind of solution? We want statistically to get a lot of different experiments, a lot of them. And this means, if I talk about a lot, thousands of droplets per experiment. So on the image here, what you can see are the key components that are usually inside the microfluidic setup itself. On the left side, you can see this microfluidic section. This usually contains the microfluidic chip itself. The chip is roughly 20 by 70 millimeters in size, so not very big, but the channels inside the chip are in the micrometer scale. I think about 100 micrometers. Also, to this microfluidic section will go all these pumps and tubing that help to create the droplets. The second part is the detection part. This is where my paper focuses more. The detection in a very large scale can be divided into two different sections. One is the electrical method, and the other one is optical. The optical one is, to my knowledge, the most widely used due to the fact that this is usually the most sensitive. In this optical way, the sensor is used for detection, the light source is used, maybe some lenses, filters are also included. Two things that are also inside one typical setup are the power supply and some communication that I won't go into the detail here. So here you can see what we built. This is an old photocopier that were used years and years ago, which means that the photocopier produced very good stability. Why we went this way is that when we started to experiment with our microfluidic device, we wanted this chip that is, I will cover it in a second. We want this chip to move in a very broad manner. So this kind of long arm enables us to move in a very wide range. But if we are sort of focused on this chip, we can do a fine tune using this XYZ table. We can move in micrometer scale there. Do this XYZ table, we have attached a camera. To the camera, we have attached a microscope lens. And this lens is looking at this microfluidic chip from beneath. The chip is held in place with this chip holder. To the chip, also we are connecting the syringe and syringe pump. There are two. One is usually we are using oil and water. They don't mix together, so it helps us to form very good droplets. And maybe not very well visible in this image, there are two small tubings that go from syringe to this to this chip. Maybe it's a little bit better visible here, where it's this green background. So there, these tubings, the outside diameter is roughly, I think, millimeter. Inside is 0.5 millimeter. So small tubings. To illuminate our experiment, we are using an LED light that is on top of this setup. And in some cases, we are also using liquids that contain fluorescent materials. So also a blue laser is used with our experiment. So a little bit about the motivation and novelty. Based on the lighting setup, the information gathered from the droplets can be divided into two kind of sections. One is sort of this backlight situation. This is similar to the experiment that you do with the microscope, that you look at your microscopic slide, there is an illumination, and you see that what is happening on this slide. This is a very typical way. It's quite similar. The other way is to illuminate the droplets from the same side that where the camera is situated. And usually in that case, the fluorescein is contained inside the droplets. This brightens up and is captured with the camera. What we found out is that when we started recording, it seemed very easy. Let's take a video of our results. However, there are quite a lot of limitations. For example, the hardware usually won't go above 90 or 120 frames per second. And even if it goes a little bit above, then the results that you get are very compressed. You don't get very detailed images. So the one problem that we tried to solve is that we really wanted to save images of our results at very high rate. The aim of our paper was to compare open source hardware imaging sensors for droplet microfluidic applications. And we analyzed results based on this backlight and laser light situations. The novelty of our setup is to use the open source hardware and software that is cheaper compared to the commercial high-speed cameras, and to achieve the recording speeds that are higher than previously reported in the literature. So the very first camera that we used was this Raspberry Pi version 2 camera, open source. This uses this Sony sensors. Usually the still resolution of this camera is 8 megapixels, but when you want to get a very high frame rate, you have to compress down this resolution. So what we did is compress the resolution down to 640 by 480. And at that case, you will get the maximum of 90 frames per second for video. However, like I said, we wanted to take images. There is one open source code available that using this code, we were able to capture raw images from the sensor at the lower resolution, 640 by 128. And the results that we captured look like this on here. So what the scale is, what we're talking about, this is 90 micrometers. So it is in the range of 100 micrometers. The lens is going really close to the channel. So we want to get a high detail of this droplet. Additional test that we made was with an additional filter and fluorescein. It is already quite difficult to capture because the filter takes some detail out of the image. Also, the fluorescein is not so bright anymore. So we can see the droplets moving there, but there is very difficult to find any details. And we compared the results with the sort of commercial camera, pulsar rays camera that goes very high with frame rate. I think at VGA resolution, it was somewhere around 750 frames per second. And here you can also see a very good difference between the technologies of the sensor. On the top one, the global shutter is used, meaning that the image is taken out from the sensor at the same time, versus the rolling shutter. Maybe you have taken some images from the car window and you see a distorted image. The similar results were captured with the Raspberry Pi high quality camera. We were expecting that, okay, maybe we're getting a better results out of that one. However, for some reason, the software didn't let us to go above 200 frames per second. So we actually got from the version 2 camera much better results compared to this high quality camera. However, with this high quality camera, the results for fluorescein measurements were much better. So to conclude, the comparison of two open hardware and one mid-range cost-effective camera sensors were presented. Previously in the literature, a frame rate up to 120 frames per second was presented. In our solution, for one camera, we were able to push it to 200 frames per second. For another Raspberry Pi version 2 camera, 665 frames per second was achieved. And also this mid-range camera was used to somewhat compare as an alternative. But at lower resolutions, this was able to actually go to 4,500 frames per second. So thank you for listening, and I'm waiting questions for everything. If something was not detailed enough, please ask.
Thank you. Is there any question in the audience or in the remote audience? Yeah.
Anton Spatlins from Riga Technical University. Thank you for interesting presentation. And the question is, how expensive is this low-cost technology? First, yeah, and second, you have mentioned about viruses in the beginning, and is it possible to discover viruses with such similar camera without additional optics? Thank you.
Yeah, thank you for your question. Let me start from the hardware costs. The typical, if we go back to this, what is contained in the setup in general. So you need this chip. Usually the chip chips that what we are at the moment using are you take for one experiment and throw away and you manufacture another one. There are possibilities to use already ready-made chips, but this has to be tuned in for your experiment. So to put a little backstory into it, every experiment is sort of manufactured sort of for one thing. It's not a magical device that does everything, but you engineer it to one thing. So the chip and everything has to be tuned for it. The same is true for the cameras, meaning that if you ask that, can you detect the viruses? I would have to say that probably yes, but the biologist has to know what they will put into the droplet and what will they expect. So if I mentioned these fluorescein experiments also that we are doing. One way to do it is that you put inside the droplet the virus, let's say, you put this antibody inside, and also somewhere is the fluorescein. And as I have understood that if some reaction takes place, the antibody reacts with the virus and defeats it, the fluorescein attaches itself to the virus or whatever is cell or whatever is inside it. So it lights up, so we can detect that, okay, the reaction took place and it worked. Now, a little bit about the cost. I do have to check because I didn't prepare for it. I know that the V2 camera is around 20-30 euros. The high quality camera is about 60 or something euros. So this is only the price of the sensors itself. You have to also account for the price of Raspberry, which today is actually very difficult to acquire, unfortunately. So not the very best way to what to achieve or how to build up your experiment. But if you get this sort of open hardware direction and you get the Raspberry and the camera, this is actually a very good place where to start. So we are talking about maybe 100, 200 euros investment, maybe plus some lenses that also cost in a range of 100 per piece. So building something at home, I would say that maybe it's not that difficult. Yeah, and not that expensive also.
Okay, thank you very much for the question. Thank you very much for your presentation.
Thank you.
And the next presentation is called Airport Wildlife Hazard Management System, a Sensor Fusion Approach, and it's going to be presented by Damian Czech from Bioseco in Gdańsk in Poland.
Yes, thank you. Good afternoon. I am Damian Czech, and I'm pleased to present the results of our research about airport wildlife hazard management at airport. This work was done in cooperation with two Polish companies related with birds protection, the Bioseco and Ecoaviation, and Swedish University Blekinge Institute of Technology. The outline of my presentation is as follows. First, I will discuss the objectives, design process, and a proposed solution. Next, I will show a prototype and obtain results. Finally, I will conclude my presentation and propose future works. The general aim of the system was to increase passenger safety without compromising wildlife preservation. The main desired functionalities are related with runway monitoring, threat and data management, and communication and interfaces. Moreover, it was expected that the system will work in real time, ensuring high reliability of detection and threat classification, and without compromising the cost of the system. The system was developed in line with user-driven design methodology, where stakeholders, future users, and designers actively participate in all stages of the system development. The expected functionalities for runway monitoring are related with mammal and bird detections, with possibility of its classification during the daylight. Identified constraints were detection range up to 300 meters with reliability of at least 90%, The information about detection should be sent to the operator in less than 15 seconds for intrusion. The system should operate during the day and night. The minimal expected size of animal to be detected is as fox light. And as an option, it was expected to classify detection during the daylight condition with reliability at least 80%. Among others, the technologies fulfilling stated requirements are thermal and vision cameras, which are chosen in this project. The solution is based on IoT and can be placed around the airport, closer or farther from the runway, depending on needs and the requirements. As mentioned, proposed solution consists of thermal and vision cameras mounted on a positioning unit. The data processing flow presents as follows. At each position of positioning unit, several frames are taken and background removal approach is used for movement detection. If something is detected, the image together with information about rotation position are sent to threat classification unit. There, the decision about threat level together with related deterrence method are taken and records are stored in database. Optionally, during the daily condition, the threat classification unit is fed with object class, for example, bird or mammal. The class is based on the image from the vision camera. Here you can see some examples of detection of a large mammal, which in this case is human, and small mammal, a dog, at different distances. As you can see, at the 100 meters, both human and dog are on both vision and thermal cameras are easily recognizable. At 200 meters, images are blurred. However, still it is possible to recognize a human and small animal. At 300 meters, it is possible to detect only a presence of a small animal. And however, the person is still recognizable on vision camera. Second general functionality related with the problem are concerned with threat and data management. It includes threat level classification on one of the three possible threat levels on runway, which is considered as high threat, close to runway, which is medium threat, and on the other part of the airport, which was assessed as a low threat. The information about management and the deterrent methods are planned in future works, are not the issue of today's presentation. The proposed threat level classification is based on an angular position of the positioning unit and the location of the detected object. As you can see on the runway, there is a high threat, closer to runway is a medium threat, and far away from the runway is low threat. The validation of the developed system was threefold. First, the system was validated under dark condition. The man of 120 kilos weight and 1.99 meters tall, and a dog half meters long and 0.3 meters tall were walking at a given distance, starting from 25 meters up to 300 meters with a step of 25 meters. The second scenario used the same person, dog, and walk path. However, during the daylight, good visibility condition. In the third scenario, the system was placed near the airport runway and tested for 39 days during December 2021 and January 2022. The results obtained during the night showed that the system can detect small animal up to 300 meters with a rate of 92%, and human up to 325 meters, also with a rate 92%, which match the desired requirement of minimum 90% up to 300 meters. In second scenario, during the daylight, the detection classification was evaluated. As a comparison, the state of the art classifier, YOLO, and Google Net Cloud were chosen. The YOLO classifier correctly classifies the human with an efficiency of 90% up to 200 meters, but in totally falls in recognition of the dog. The Google Net classifier met desired requirement in recognition of the human within whole monitoring area. Moreover, it was able to recognize the dog up to 200 meters. However, the acceptable efficiency was obtained up to 100 meters. During the real test at the airport, there were no mammals observation reported, nor by the system or the airport staff, within field of view of the system. However, there was 61 observation of birds. They were reported by the additional system for birds monitoring, the Biosecure Birds Protection System, BPS, and they serve as a reference. The BPS was set up near the thermal and vision cameras system, so they have particular common field of view. Each observation of BPS was also recorded and detected by the thermal and vision system presented in this work. In case of classification, the YOLO classifier fails to recognize birds. The GoogleNet cloud was able to classify birds with expected efficiency up to 150 meters. However, the Biosecure BPS classifier recognized all birds detection in a range of up to 300 meters. In this work, we present solution affordable for even for medium and small airports, ensuring wildlife hazard management during the day and night. Obtain detection efficiency of small animals like dogs at a distance of up to 300 meters and a larger object like humans at a distance of up to 325 meters was 92%. During the daylight condition, by applying GoogleNet Cloud, the system classified human with an efficiency of 92% up to 300 meters. The dog was classified up to 100 meters with an efficiency of at least 83%. By means of Biosecure BPS classifier, the system correctly identifies birds at a distance up to 300 meters. Thank you for your attention. Do you have any question?
Do you have any question from the audience or also remote audience? Yes.
Hello, I have one question. Did you discover exceptions, for example, if small insects are close to the camera? Is camera recognize this as an object, dangerous object or not?
Okay, thank you for the question. In vision camera, it could be an issue. However, we also use this thermal one. And in that case, we do not observe false detection due to the insects. And in case of vision camera, we also have the classifier, which we fed with these images. And if there, it was trained to skip the flies. I mean, we use this BPS Biosecure classifier, which was trained directly to detect the birds.
Thank you. I have also a question.
Yes.
Did you quantify the difference in time in processing time of for the same frames, Google Net or versus your algorithm?
We do not verify this straightforward, but however, the time needed to inform the operator was 15 seconds. So in our case, it was not a problem.
Okay, this is my question. This is a very interesting work. In fact, I was remember that one of our students in telecommunication engineering was directing the airport in our city, and one of the most important tasks in his things to do was to take care of the falcons and all the animals that work in keeping clean the runaway. So it's really interesting to have technological solutions to help the falcons, not only send the falcons when they are needed, not every day.
In other airports also, it's often a problem when they send one team to one part of the airport and the other there's a birds fly to the other part. So still there is a problem. And with our solution, despite the detection system, we also provide deterrence systems. So the team with Falcons can go on the one side of the airport, and the deterrence can be remotely set up or start on the other part. So the birds fly away from the airport, not move around the runway. Okay. Thank you very much.
Thank you very much. And then the fifth presentation is called Numerical Modeling of Humidity Behavior in Electronics Housing, and it's going to be presented by Sigimantans Staliulonis, thank you, from the Kaunas University of Technology here in Lithuania. Limitations in pronouncing the names, but also I'm having limitations in reading the names because of the age. You know, in some years you are going to experiment the same.
Good afternoon. My name is Guillermo, and thank you for introduction. So I will present numerical modeling of humidity behavior in the electronics housing. It's kind of combination and related with electronics, but I will focus more from the humidity is related more with reliability point of view. Okay. So here's the agenda, and I will tell a little bit of background and motivation why I'm doing this and why it's important, and then I will give a bit of theory and modeling of humidity inside the electronics enclosure, and then the second example will be modeling of humidity and condensation based on the industrial application, namely water pumps. So why is it important? So we have many electronics used outside and also which are exposed to harsh environments like wind turbines, like hearing aids. Also, in the for example, people are also sweating, and it's also kind of a salt and harsh environment. And then we have like water meters, water pumps. So, and basically exposure to the harsh environment leads to a number of failures. Basically, electrochemical migration, conductive anodic filament, and migration under conformal coating, galvanic corrosion of bone pad, and gas corrosion of silver. And we have also alternation of material properties. Then we can get also short or open circuit. And basically these failures are mainly caused by humidity and condensation, which can be found also like on chassis. I show some examples, like on components we can get, like on metallic parts we can get condensation, and this also causes a big problem. Basically about 20% of electronics failures are caused by humidity, and nowadays this number is more increasing because due to miniaturization of electronics and etc. So there are basically there are 4 means used to control the humidity in electronics. Basically control of absolute humidity when we use a desiccant like silica gel. Then we can control the temperature, means that we can control the relative humidity. And then we can avoid condensation by using a heater. And then we can use metallic encapsulation, which can prevent getting of humidity through the walls, but it's quite expensive. Then we can use a potting or coating of electronics, and then we can prevent for a while the humidity, but still we cannot prevent for a long period because we can, these materials also absorb some humidity, and we can get humidity ingress through the interface between PCB and coating material. And this, of course, means also based mostly on the experiments, not on the scientific knowledge and good understanding of moisture, because it still is a challenge now to understand nowadays to understand the humidity problems in electronics. So my work focuses more on the modeling, also to develop like kind of numerical modeling in order to predict the humidity in electronics. And of course, it goes together with the experiments. And here's the concept of the work, what I'm doing actually. So first we have a mathematical model based on the coupled partial differential equation, which describes transport of heat and transport of mass, diffusion and convection. Then we go to the numerical approach for solving mathematical model. We can use also IC approach or high fidelity approach, like finite element method, CFD. And then we use experiments in order to compare this and to validate the code. So in this case, in this work, I will focus on the IC approach because it's quite flexible and fast to use, and so appropriate to use for companies when you need to see the trend where where the humidity moves and so on. And so I will move to modeling of humidity inside electronics enclosures. Actually, this work is also continuation of my PhD. So, but now I'm doing a postdoc. So normally we have enclosure where we can have many kind of mechanism of humidity, like condensation, convective vapor transport, diffusion through the polymer materials, then absorbed water, and then so like retained water, evaporation, and then we can have flow through the whole of the enclosure. But in this case, we started from the very simple case. Let's say we have a plastic enclosure, and then we only consider the convective thermal and vapor water transport outside and inside, and then through the wall. And then we have heat conduction through a wall. And if we assume if we make some assumptions for modeling, then if we have like temperature uniform over the outer and inner surface of the box, and then we assume that we have convection inside the enclosure and in the atmosphere to be sufficient to maintain the spatially constant densities of water vapor and temperature in each two regions, then we can use this box like this one, like wall separating two regions, and then we can simplify the modeling in this case when we have empty box. And in order to model this, we use a basis for modeling like a heat transfer in solid, and then we have mass transfer is fixed second law, and then convective heat transfer defined by Newton's law, and then convective mass transfer, which is similar to the convective heat transfer. And then Henry's law, which is where we have this actually theory is used to attain the continuous field of like instead of concentration, we can use pressure, and then vice versa actually, because normally there is a discontinuity between air and the solid material because we have very different concentration levels. And I will show a circuit for modeling such simple case. Here's represented like outside of box. Then we have a voltage term, like instead of pressure, and then we have temperature circuit to solve the thermal field, and then here for moisture. And these two circuits are coupled, and you can see that also this represents in 1D dimensional wall of box and then inside of the box. So with this simple case, actually we can model we can get some good results, which I will show you in the next slide. And so this coupling is performed by using temperature from nodes as an input for the moisture circuit, and then we can solve different field of pressure where we can calculate concentration and then we can calculate the relative humidity. And we used to solve these circuits by RC approach, of course, as you see, and then we use a modified nodal matrix analysis, which is based on the implicit backward Euler, and then we solve this circuits using this approach. Before moving to non-isothermal case, we actually already did with the experiments. My colleague also previously, when I was PhD student, did the experiments on the box, realistic box, I mean, taken from Phoebox, and we did a moisture buildup, and when we have constant temperature all the time, we only investigate moisture. So you can see with this approach, and we can get a good alignment with experiments. So it gave us a good promise. Actually, we can move on and continue our studies in that direction. And then and this also was presented in the paper. And then I would like to show some moisture modeling on the non-isothermal case when we have initial conditions 25 and then initial relative humidity 40%. Then box was exposed to 74% and 35 Celsius. And here we take the same box, but then we investigate two different materials, namely polycarbonate and then 30% glass fiber reinforced polybutylene terephthalate, which is called, the abbreviation is PBT30 GF. And then here I would like to show the interior temperature response. Of course, it's pretty quick, and there is no big difference actually. So that's why I show one of, like one close to each other, because the thermal conductivity of these materials are very close. So that's why we don't see a big difference, and it goes quickly. Here we can see the response of humidity inside. So we have ambient 74%, and then of course, here's the full scale, and then here's the zoom scale, because up to this point, we have actually non-isothermal conditions. When the temperature stabilizes, then we have isothermal conditions. So we have two processes. And in the beginning, when we have zoom scale, then of course, the relative humidity drops because temperature increases inside, so it drops. And dependent on the material, actually PBT material has a lower diffusivity and then solubility. So relative humidity drops more, and in case of polycarbonate we have a bit higher relative humidity because due to diffusion coefficient, it can the moisture can flow faster through the wall. And here the blue one and red lines are represented by the dew point temperature. Dew point temperature is defined by the amount of moisture, like in the air. So, and it represents, what is the temperature, where we can get a condensation. So, as you see, it starts increasing from the beginning, because the moisture, the concentration of moisture is increasing inside the box. And here I would like to show the concentration profile, which is, of course, behaves. And if I go a bit back, I forgot to mention that in the beginning, when we have a non-isothermal case, we have sudden changes. And then when we have an isothermal case, it starts the relative humidity and concentration starts increasing slowly, because it takes time because moisture processes are much slower. It takes days sometimes when we have isothermal case. And here we can see the same with the concentration, that it starts increasing. Concentration increases faster in case of polycarbonate material, which is actually, and this real box is made of polycarbonate material. And so to imagine how big difference is between like polycarbonate material at 20 Celsius temperature can absorb up to 5 kilograms per cubic meter, actually water vapor, while air can contain only 17 grams per cubic meter. So we can see, a big difference actually, how much solid material, polymeric materials can absorb moisture compared to the air. And then we applied a heating. Only PC material is considered, just to show, what the difference we get. And of course, when we have a heating of 1 watt, we have a lower relative humidity compared to no heating. And then, of course, in case of heating, we have a bit higher dew point temperature. And here I show the zoom scale that is slightly higher because the temperature increases the diffusion coefficient, because it's temperature. Diffusion coefficient is temperature dependent. And then I would like to move to a more industrial application, like a water pump. For example, normally water pumps are made like motor, here electronics sitting on top of, and the electronics is made, of course, of polymeric materials mostly. So, and there are wires connecting actually to the motor. So we can represent the water pump like using a worm enclosure, which represents the electronics box. Tube represents more like connectors between motor and the electronics box. And cold enclosure shows the, actually is more to show the motor, So normally water pumps also can have about 4 Celsius degrees actually temperature. So, and we normally get a condensation in the motor. So, and here's the IC thermal circuit to model the temperature field. So here we have a cold temperature of cold water, and we have we represent it in 1D actually in this case, that we have thermal flow through the motor wall, and then here's the representation of the tube, and then here's the wall of warm chamber enclosure. So, and then here we have a moisture circuit, or in other words, we can call it a hygroscopic circuit, where we have a moisture flow through the plastic of warm enclosure, and then we have only moisture transport through the tube. And here we neglect actually through the motor wall, because metals doesn't absorb moisture, so we only have this. And then we applied ambient conditions taken from the B2 standard climatic conditions, where it's represented like climates from Australia, from Asia, or whatever, actually from different regions. And then we applied 2 watts of heating in the warm enclosure. And here's of course a response, how the temperature is responding to the ambient and also to the heating. And we see that the profile of temperature is very similar. And then we can see what is happening with the relative humidity. Of course, relative humidity drops actually because of the heating. And then we have here mass accumulation in the cold chamber. We can see that water is accumulating in the cold chamber, which means in the motor. So after a while, we can get actually a swimming pool. Like I'm kidding, but we can get like this after a while. And here I show the algorithm how we can calculate the mass condensed in the cold chamber. And I would like to show, of course, come up to the conclusions. Of course, thermal time constant is much smaller than the time constant of moisture transport. Therefore, heat is transferred quickly, and then the moisture ingress may take a very long time. And the absorption and desorption mechanism are very important because it causes a sudden and large change in the concentration. And here where we can have big problems actually with moisture-related problems like corrosion, and after a while, because when we have a sudden temperature change, the concentration really changes due to absorption and desorption mechanism. And of course, then the code shows the quite good flexibility of coupling different circuits for different physics. And then it's very simple and fast to implement in the model. So. And yeah, and then one more thing, diffusion coefficient of polycarbonate material is about 5 times higher than the PBT material at this temperature. So the project is funded by the Research European Social Fund. And yeah, here's about me a little, that I studied I received master in electronics engineering. Then I received PhD degree in mechanical engineering from Technical University of Denmark. And then I was focusing on the development of semi-empirical models for predicting climate inside the electronics enclosures. This was carried out with the close collaboration with Danfoss, Grundfos, LTEC, and other companies. And then after completion, I was working at Force Technology. And then I came back again to the academia and having a postdoctoral research. Thank you for listening my presentation.
Okay, thank you very much. Do you have any question from the audience? From the remote audience, no questions? They are not very active.
Not from Monday.
In fact, I have no questions because it's so far from my knowledge that it's difficult to do any interesting or even no and stupid question where you are not.
I think there is no. There is no.
But I think that what is very interesting is the full design of this session, because it's a combination of different situations that in fact we need all of this to create a final application. So it's important to check about the distance and to improve the quality of the sensors to go farther away. It's important to have some notes to remember.
It's okay.
It's important to optimize the energy consumption. It's important to be sure that we integrate everything in an enclosure that defend the system against the outer effects like humidity, and probably the people that work in the airport know that it's important to keep these systems completely dry.
Exactly.
And also improving the measuring techniques are interesting for getting better and better performance in our designs. So thank you very much to all the attendants. Oh, we have a question in the audience.
One stupid question.
There is no stupid. Maybe I can give a stupid answer.
Okay. Why you choose for your experiments only two temperature degrees, 25 and 35? For your experiments, I think maybe it would be interesting to take wide amplitude, non-constant temperature, but like in real condition, from very below zero and to maybe above about 50-60 degrees. Maybe it would be another results. Yeah.
Yes, it's actually we already did that with some experiments in order to provoke the condensation evaporation, because it's very complex, you know. So that's why initially we wanted to take 20 Celsius and 25, because, you know, we just to see, you know, what is happening, what we can get with this modeling, actually, whether it makes sense to continue or not, you know, or doesn't make sense to do it at all. So that's why we started initially from this, and but now then we wanted to exclude the condensation evaporation. Condensation is one thing, but when we start evaporation, it's a very complex process. Actually, it's very difficult to predict. There are a number of things which we have to consider, and it's not that easy. But we have already carried out some experiments, and there are also some of my experiments presented in another conference paper. So I would be glad, you know, to share if you would like to read it. So we did from 20 to 50, and then we go to zero, just to provoke condensation in metallic box like aluminum, made of aluminum, and then plastic boxes. First of all, we took a simple case glass jar in order to see, you know, what is happening if we have two different materials. Because glass jar doesn't absorb moisture, and then metallic materials doesn't absorb. So, but plastic absorbs, and then we get some interesting results. For example, we think that we may have condensation at certain level, but we don't have. because there is absorption to the plastic box. But if we go vice versa, we may have, number of things, So that's why I mentioned in the beginning of presentation that it's very important to understand physics of moisture. So it's in order to develop something further with the modeling. And that's why, like in companies, I know they sometimes take from the experience what they have in the experiments, and they say, okay, I think it's fair enough to have this. If you don't go below or above, this limit, then we are okay. And they don't care so much because it takes a lot of time also to investigate. You need to make a decision now, but not tomorrow. Let's say if you develop something.
Yeah, that is why I was wondering.
Exactly.
About only to this.
Yeah. Indeed. You're welcome. Thank you.
Thank you very much. And thank you very much to all the attendants, to all the presenters. We were able to keep the time of the session, and also we were able, the presenters were able to keep the attention of the audience just after finishing the lunch with us. What I think is a good job, a good target, a good performance in your presentations. Thank you very much to all of you, and we are now time for coffee break. Thank you.